The first exam is going to be on Wednesday. And we'll start the class meeting with some question and answer time. Then we'll take the exam the last 90 minutes or so of the class meeting. Please make sure that you have a working webcam on your computer so that you can turn on the webcam so that I can see you guys and we have a proctored testing environment. So what we'll do is we will meet here in Collaborate Ultra, and we'll turn on our webcams, and then I will email the exam to you, and you will have that exam, and you will complete it on pencil and paper. Okay. After that, you will scan your papers using your smartphone with scanning software like Adobe Scan or Cam Scanner. So there's other things that are comparable to them. So whichever one you like will be fine. During the exam, and I'll let you know when. So we'll have 90 minutes for the exam, and I'll say, well, everything's got to be uploaded by this time. So as a bit of warning ahead of time, don't use a flatbed scanner. If you have to use a flatbed scanner, have a smartphone or something, make sure you set the resolution way down on the scanner, because if you don't, your file will come out to be really huge, and it won't upload to Dropbox. Okay, or it'll take forever to upload, or your internet connection won't be able to handle it, or something, some other technical glitch. So let me write that down. Don't use a flatbed scanner, or if you do, set the resolution down. Come on. Do not use a flatbed scanner. If you have to, set the resolution way down so your scan file is not that big. Because again, if it's too big, it won't upload. There's something else I wanted to mention. Oh yeah, PDF document, one PDF document. During exam, you can use a basic graphing calculator, but no internet-enabled devices. No smartphones, no laptops, no tablets. No. Sometimes these graphing calculators are internet-enabled, so you can't use those either. You can have one 8.5 by 11 page of handwritten notes. Okay, so any notes handwritten, no Xeroxes or scans or whatever else, just stuff you write out by hand. Okay, so that's the rules for the exam. The exam covers the exam covers 3.1, 2.1 and 2.7, including section 2.6, 3.1, 2, and 4. Okay. Questions about anything pertaining to that? Any questions about things pertaining to that? All right. So, sorry, go ahead.
Yeah, for the handwritten notes,
Uh-huh.
is it single side, 8.5 by 11, or both sides?
Both sides, 8.5 by 11 paper, I guess.
All right, thank you.
Yeah. Anything else? All right. So last time, we went all the way up to section 3.2, and then finally we made it to section 3.4. So I want to, since we have a little extra time today, I want to talk a little bit about section 3.4. Sorry, section 3.3. So in section 3.3, so before we get into 3.4, let's talk about 3.3 a little bit. In section 3.3, given R of t continuous for a less than or equal to t less than or equal to b in 2D or 3D. Okay, so here's a picture in 2D, but it could be in 3D or what have you. So this is R of A, and this is R of B. And then that's R of T, going from R of A to R of B. The length of is the integral from A to B of the scalar function r prime of t dt. Why? Okay, well, the calculation and description of y is not that tricky, actually. Um, so first, we're going to estimate the length of the curve. So split the interval a less than or equal to t less than or equal to b into n subintervals of length b delta t equal to b minus a over n. Right, so you have the standard setup. Right, so like this. Right, T1, T2, T3, T4, T5, so on and so forth. Right, where T0, well, where Ti is equal to A plus I delta T. So you've got this standard setup on the t-axis, right? You split that interval up into subintervals of equal length. Now you plot those points on the curve. So here's that curve for r of t. And we're going to be doing a lot of this semester. Setting up new types of integrals. So there's r of a. Let's do a different color here. So r of t1. Now these don't have to be evenly spaced, and they're probably not evenly spaced, but it doesn't really matter. R of t4, r of t5, r of t6, r of t7, and then this will be r of t8 or something like that. And then you connect those points. You connect those points with straight lines. Like that. So plot these points along the curve. And connect with straight lines. Right? The sum of the lengths of the straight lines approximates the length of the curve. Right? Clearly. The sum of the lengths of the straight line segments estimates the length of the curve. As delta t approaches 0, the estimate gets better and better. The smaller delta t gets, the better of an estimate you get. Yeah? I mean, picture that as, very straight line segments. Now, of course, when you watch television or play video games or, whatever else you look at on a digital screen, you don't have like smooth outlines that you look at in a picture. They're actually, pixelated little, not just straight lines, but horizontal and vertical lines, right? In a pixelated sense or whatnot. So there is no straight line. It's all just the tinier the pixels are, the smoother the line looks. Right? That's the idea here. Right? The smaller those lines get, the better the estimate gets. Therefore, the actual length of the curve is the limit as delta t goes to 0, right? Or as n goes to infinity, of the estimate. Okay, well, let's look at the algebra of that estimate. How do we express that estimate algebraically? Well, right, so here is r ti, ti minus 1, say, and here is r of ti. And the coordinates here are the x of ti, y of ti, z of ti. So we'll do this in 3 dimensions. X ti minus 1, y ti minus 1, z ti minus 1. So you have this parametric curve in terms of t, and we'll call this line segment si. Right? And the length of si is, well, you just use the distance formula, right? So it's the change in x. So I'm just going to write delta x. The change in x squared plus the change in y squared plus the change in z squared square root. Right? If you're in 2 dimensions, there's no delta z. There's just delta y and delta x. So that's the length of si. Change in x, change in y, change in z, all squared, added together, square root. Okay, so the length of the curve is the limit as n goes to infinity. The sum, I equals 1 to n, of s, the length si, length of si, which is equal to the limit as n goes to infinity. The sum, I equals 1 to n, of that expression there. Delta x squared plus delta y squared plus delta z squared. Now, this would be an integral setup, a Riemann sum setup. But what's missing? Why isn't it a Riemann sum yet? What's missing here in order to make it a Riemann sum in terms of t? Right? X is in terms of t, y is in terms of t, z is in terms of t, so that's all good to go. This is all in terms of t, but what's missing here in order to be a Riemann sum for t? What would you need there? Certain delta t. Right? A Riemann sum for t is the limit of the sum of a function of t, right? This is f of ti, right? F of ti, whatever this f is, times delta t, right? That's the basic form for an integral. The integral from a to b of f of t dt is, by definition, the limit as n goes to infinity, sum I equals 1 to n, f t I delta t. This is the definition of the definite integral. Right? Why is this capital S used for an integral? Well, I don't know if this is true, but S is the first word in sum. And a Riemann sum is a skinny sum, so it's a skinny S. So I don't know if that's really the thing, really the reason. But my dad always used to say, well, if you don't know a better reason, then take that as a truth until you know otherwise. So that's the definition of the integral. The integral of f of t from a to b is the limit as n goes to infinity, sum fti delta t. This is all fti. The x, y, and z are all in terms of ti, because these functions are in terms of t. All that's missing there is a delta t. There is no delta t there. But I can get a delta t inside there. Make that blue. I can get a delta t inside there. What I do is multiply by delta t over delta t. Like that. And then bring the denominator inside that square root. So it's the limit as n goes to infinity, I equals 1 to n. Delta x squared plus delta y squared plus delta z squared 1 over delta t squared delta t. I brought that 1 over delta t inside there, inside the square root, so it gets squared. All right, square root of delta t squared would be delta t, because it's positive. All right, now I distribute this through here, and I get the limit as n goes to infinity. Sum I equals 1 to n square root of, just distribute this through there, and then, distribute the square over the division, and I get delta x over delta t squared, delta y over delta t squared, delta z over delta t squared times delta t. Now, this is f of t I. This is all in terms of ti. So it's just some function, f of ti, and there is delta t. So now it's a Riemann sum. Now it's a Riemann sum. So this turns out to be an integral from a to b of this function. But what is this function? As n goes to infinity, which is as delta t goes to 0, as delta t goes to 0, the limit as n goes to infinity, which is the same as the limit as delta t goes to 0, well, change in x over change in t. As change in t goes to 0 is what? What is that? What is this? Change in x over change in t as change in t goes to 0. What is that? Y'all know. It's maybe not usually written that way. Sometimes we write it, well, usually when you first see it, it's written like this. The limit as t goes to a, f of t minus f of a over t minus a. Right? That's the change in t. That's the change in f. And that's the change in t going to 0. So t changes around a. So the change in t going to 0 around a. So what's this expression? You guys there? What's this? What's that?
Would it just be delta x over t?
No, it's f. It's f. It's df dt, or f prime of t, or f prime of a. Sorry, in this case, it's the derivative. Right. So that's what this is. It's dx dt. Dx dt squared plus this dy dt. Change in y over change in t squared dz dt squared all that dt. But then this is the length of the vector function So it's the integral from a to b, the length of this thing, dx, well, I'm going to write it in terms of x prime now, x prime of t, y prime of t, z prime of t. The length of that vector function. But that's just r prime of t. So that's the length of the curve. The length of r of t for a less than or equal to t less than or equal to b. Now, when you're moving on a straight line, so now if t is time, in, you know, some units, seconds, hours, minutes, etc. In some units, if t is time in some units, then the integral from a to b of r prime of t, or sorry, if t is time in some units and r of t is equal to the position of a moving point in 2D or 3D at time t, then the integral from a to b of f, or not f, r prime of t dt is equal to distance traveled for a less than or equal to t less than or equal to b. So length becomes distance traveled. Distance traveled how? Distance traveled along a line in one direction. Or the line curves around and all that sort of jazz, right? The line's curvy and loopy and it's doing whatever else it's doing, but you're still just going in a straight line. Sorry, you're going in one direction along a one-dimensional curve. The distance traveled, right, along the one-dimensional curve r of t embedded in 2D or 3D. I mean, the curve is embedded in 2 dimensions or 3 dimensions, but the curve itself is a one-dimensional thing. Along in one direction along the one-dimensional curve. Right, so there's your curve, and you're just going from here to here. And that's the distance you travel. Well, distance over time is what? Not velocity. Distance over time in one direction is the rate of change of distance in one direction with respect to time is what? Rate of change of distance in one direction with respect to time is what? What do you call it? Not velocity, but
Speed.
Speed, exactly. That's your speed, right? 25 miles an hour, or 60 miles an hour, or 70 on the interstates in Ohio, or whatever it might be, is speed, right? So if r of t is position and r prime of t is direction, is tangent to the positional curve, and the length of r prime of t, right? So, sorry. So if r of t is position and r prime of t is tangent to the curve, positional curve r of t, then r prime of t is in the same direction as velocity. Right? Well, the length of velocity or the magnitude of velocity is speed. Right? So we have the direction of velocity, and the speed is exactly that length. So since r prime of t is the speed, and r prime of t is in the right direction, for velocity, we now get that. It's a r prime of t is equal to velocity when r of t is equal to position. I mean, it actually takes some doing, like, to actually establish the fact that if r of t is position, right, and t is time, if t is time, r of t is position, it takes some discussion to establish the fact that r prime of t is velocity. It's not a simple thing. Yeah, when you're doing it in one dimension, when you're doing it just along a horizontal line, when you're talking about, a function representing position along a horizontal line, like you do it in Calc 1 and Calc 2, there's not too much to discuss. It's just kind of obvious that it's the velocity, because it's the rate of change of distance in one direction. Well, I mean, here, and there's only one direction because the whole thing is lying in one dimension. But here, I mean, it's a more complicated thing because it takes knowing what the length of a curve is. So, and doing that required, like, doing some fancy integration setup. We're going to be doing a lot of that this semester, fancy integration setup that will apply to different physics scenarios. All of the math that you do in Calc 3 here, all of this math, it's all for physical situations. Okay, it developed hand in hand with the physics. Right, there was not so much of a sort of clear delineation between the the fields of inquiry that are math and physics in the past. There wasn't quite such a clear delineation. There was, I mean, a delineation, but the two went hand in hand. Okay, and then, through similar arguments, through other arguments, which use Newton's second law, r double prime of t is acceleration. So now we've got the setup that we want. R is position, t is time, r is position, r prime is velocity, and r double prime is acceleration, and the length of r prime is speed. Okay, so now, that we have that under our belts, let's take a look at these problems in section 3.4. So number 158. So given the following position functions, find the velocity, acceleration, and speed in terms of the parameter t. So e to the minus t, t squared, tangent t. So section 3.4, 158. e to the minus t, t squared, tangent. All right, so that's position. Time t, find velocity, speed, and acceleration at time t. Okay, so, well, velocity, v of t, is just the derivative, r prime of t. So that's minus e to the minus t, 2t, and then derivative of tangent is secant squared t. All right, so speed is, well, it's the length of velocity, or the length of r prime. So that is e to the minus 2t, 4t squared, secant to the fourth t. And then acceleration, a of t, well, that's r double prime of t. So here we get just e to the minus t, 2, and then 2 secant t, secant t, tangent t. So this is equal to e to the minus t, 2 secant squared t, times tangent t. Okay, so we've got distance or displacement or position, velocity, speed, and acceleration. One 162. So 162, so this is sine t, cosine t, t. So this is that, well, the helix, although they don't have enough of it drawn that you can really see it. So in 62, all right, so position at time t is r of t equal to cosine t, t sine t, or sine t and cosine. So this is the helix that is centered on the y-axis. So if you look at the cylinder of radius 1, centered on the y-axis, all right, here it starts here at t equal to 0, and here this helix is winding this way. Going in that direction. So that's position. And then find velocity, speed, and acceleration. Well, what's interesting about this helix in this form Yes, this is cosine t 1 minus sine of t. So that's velocity, and then the speed is the length of velocity. So here it's cosine squared plus sine squared plus 1. Right? Cosine squared t plus 1 plus sine squared t. All right, which is just square root of 2. You know, miles per hour, meters per second, whatever you got going there. But what's cool about that is that's a constant. So that's that one's interesting in that the speed, the rate of change of position along the curve is a constant. So one can actually calculate the arc length there easily enough because this quantity here is just a constant. Normally that integral is like a notoriously tough one that you can't really solve too easily. So that's a speed, and then acceleration, constant. It's unusual. Acceleration is r double prime of t, so this is minus sine t 0 minus cosine t. Right. So that's another just basic problem there, but it's taken into account this helix, which is an interesting case. 183. Let's see. Is there anything else interesting here? Seems like the discussion assignment is pretty slim here. Well, let's take a look at 163 here. So here we have a position function r of t where the the coordinates are done by polynomials. So look at the speed function. At what time is the speed minimum? I mean, that speed function is really important in analyzing motion in space. Sometimes even more so than the velocity, because sometimes more interesting questions are answered by speed. So t squared 5t, t squared minus 16t. Alright, so that's position at time t. So at what point t, at what time t is the speed slowest? Well, the speed, so velocity, is r prime of t. So that's 2t, 5, 2t minus 16. So speed is equal to the length of r prime of t. So that is 4t squared plus 25 plus 2t minus 16 squared. Let me make sure I got that right. Yeah. So this is equal to 4t squared plus 25 plus 4t squared minus 32, 64t plus 2 to the 8th, 256. 16 times 16 is 256. So we've got 4t squared plus, 8t squared minus 64t plus 2,281 meters per second, miles per hour, whatever we got going here. All right, so how does one? So I mean, think about what kind of function this is before we ask what's the global minimum of this function, right? Where would the minimum of what kind of function is this, right? Notice the speed, of course, is a scalar function. What kind of function is? So forgetting about the square root for a second, what's that? That's just a what? What type of curve is that?
Well, it's just parabolic.
Yeah, it's just a parabola. So, the minimum of a parabola, I mean, we know all about that. That's, where it bottoms out. So with the square root of a parabola, I mean, the square root function is an increasing function. So wherever the minimum of the square root function is where the minimum of the inner function is. Right? So the parabola has its minimum at t when we'll take the derivative of that. 16t minus 64 is equal to 0. Right, so that's t equal to 4 seconds. Or equal to 4, unit time units. All right, so parabola on the inside. Of the square root. So the minimum of a square root of f is where the minimum of f is. So we just had to find where the minimum of that parabola is rather than fussing with, taking the derivative of this, composition of a square root with a polynomial. Really the most interesting, I think, example, simple example is with the elliptical movement. And I know I did that. I'm sure I did that as an example, didn't I? In the lecture. Yeah. So here it is. So with the ellipse, right, with an elliptical path, that's really the most interesting example. You have 3 cosine t, 2 sine t. So that's, you're going from 3 to minus 3 on the x-axis, 2 to minus 2 on the y-axis there. And then you calculate the velocity here, and then the speed. And the speed function looks like this when you simplify it. It's the square root of 5t squared, or 5 sine squared t plus 4. And sine squared is between 0 and 1. But you know exactly when it's 0, and you know exactly when it's 1. It's 0 at the multiples of pi. And it's 1 at the odd multiples of pi over 2, right? So at the extremes, on the x-axis, at the large radius of the ellipse, that's when the speed is the slowest. And at the short spots, the short radius of the ellipse, that's when the speed is the fastest. And, when you talk about, planets orbiting, one body orbiting, like a planet orbiting a big sun, a big star, something that's much more massive than the planet, classically, when you analyze that, classically, not that it's exactly right, but it's right up to some small perturbations. The orbits are elliptical. And, where the planet is traveling fastest is when it's at the furthest or the closest spot on the ellipse. And when it's the slowest is when it's on the furthest spot of the ellipse. So, of course, the sun, where it's orbiting, isn't in the middle. It's at one of the 2 foci of the ellipse, but that's more than we want to talk about here. But that's the most interesting example, simple example at this point. That and the helix. All right. There's 163. The next problem is 183, but maybe there's something else that's interesting. person on a hang glider spiraling upward. Yeah, so that's a helix type problem. Path is similar to that of a helix, although it is not a helix because this is 3 cosine t, 3 sine t, and that's t squared. So it's a helix that goes up faster. Well, I don't know if that's exactly correct from a physics standpoint, that model. Oh, that's another type of thing. We'll go to 183, I guess. So the acceleration of an object is given by a of t equal to 0I plus tj plus tk, so 0tt. The velocity at 1 second is 050, and the position at t equal to 1 second is 000. Find the object's position. So, using antiderivatives, you can, you can do this stuff in reverse. So, acceleration was equal to 0, 1, 1 0 tt at time t. The velocity at time 1 was 050, right? And position at time 1 is 000. And then it's asking you to find r of t.
Yeah. No, I just got done rehabbing. I know. I was just specifying what rehab was. You know, I got the kid from Milwaukee. Yeah, you got it to your spot, bro.
All right, so it's like that Geico commercial, right? Flo, you're not muted. So velocity. So find r of t. Velocity is going to be the antiderivative of acceleration, right? V of t is antiderivative of a of t dt. Not integral, antiderivative, right? Integral, you've got, you've got limits. The integral from p to q of a of t dt. This is antiderivative, right? It uses the same symbol, but that's because of the fundamental theorem of calculus. Because integration can be evaluated using an antiderivative. That's why we use the same symbol. But of course, it's not the same thing. So velocity is the antiderivative of acceleration, which is the antiderivative of 0 t dt. So this is going to be 0, 1/2 t squared, 1/2 t squared, plus you always get an arbitrary constant when you do the antiderivative, right? And that arbitrary constant is important here because it's going to be determined by this, right? So that allows you to have a velocity function such that v of 1 is 5, 050. So now 050 is r of 1. So you're told that, you're given that 050 is r of 1, but then or v of 1, sorry. 050 is v of 1. But we know from here, from this, that v of 1 is 0, 1/2, 1/2 plus c. So we subtract this from that. So 0, 9/2 minus 1/2 is equal to c. So v of t is therefore equal to 0, 1/2 t squared plus 9/2. And then 1/2 t squared minus 1/2. So that's v of t. And then position is the antiderivative of velocity. So then r of t is the antiderivative of v of t. So this is the antiderivative of 0, 1/2 t squared plus 9/2, and then 1/2 t squared minus 1/2 dt. So you have 0, antiderivative here, 1/6 t to the third plus 9/2 t, 1/6 t to the third minus 1/2 t, plus arbitrary constant, d in this case. How do we find d? Well, we're told that r of 1 is equal to 0, 0, 0. But using this right here, using that right there, r of 1 is equal to 0, 1/6 plus 9/2, 1/6 minus 1/2 plus d. So this is what? So 0, 0, 0 is equal to 0, so 27, 28 over 6. 6 minus 1/2 is minus a third, right? 1/6 minus 3/6 minus 2/6, so minus 1/3 plus d. So you put this over here, so 0, and then 28 over 6, 28 over 2, 14 thirds minus 14 thirds, positive 1/3 is equal to d. So r of t is therefore equal to 0, 1/6 t to the third plus 9/2 t minus 14 over 3, and then 1/6 t to the third minus 1/2 t minus or plus 1/3. So that's how that works there. Okay. So, given position, you find velocity and acceleration by taking speed, by taking derivatives. And given acceleration, you can find, velocity and speed using velocity and positions using antiderivatives. And that's interesting because, acceleration, because it's because of Newton's second law, acceleration is a force in a certain direction which is felt, and that is something that can be measured. So you can measure acceleration over time, and assuming you can measure it accurately, you can reconstruct velocity and position over time. Right? So it potentially has, some interest in a physics setting. That there. So that's 183. 194. Anything interesting here? So more than just this, more of the same in 194. The position vector function r of t. Find the position vector function r of t. Given a of t equal to these things here with v of 0 and r of 0 given there. Mm, 196. 194, I mean, that's just more of the same. I'm thinking, is there anything else that's interesting? Well, let's do 194. So acceleration is 1 e to the t, and I guess this is in 2 dimensions. Yeah, 1 and e to the t. And then v of 1, or v of 0 is 0, 2, and r of 0 is 2, 0. Find r of t. So v of t is antiderivative of a of t dt, which in this case is t e to the t plus c. So then 0, 2 is v of 0, and then over here, which is 0, 1 plus c. So 0, 1 is equal to c. So v of t is therefore equal to t e to the t plus 1. So then r of t is antiderivative of v of t dt, which is 1/2 t squared plus e to the t plus t plus d. And then 2, 0 is r of 0, which in this expression here is 0, 1 plus d. So 2 minus 1 is d. So r of t is 1/2 t, oops, what did I do here? That's a comma, not a plus. 1/2 t squared plus 2 e to the t plus t minus 1. So there's your position function. Okay, so that's the basics of motion in space. Right? Position, velocity, speed, and acceleration, and all the basic mathematics that you can do along with it. Okay, so let us take a 10-minute break. It's 7:38, so let us come back at 7:48, and then we'll start in on section 4.1, and then after that we should be able to do most of that. Well, let's take 10 minutes, come back, let's ask some questions, then we'll go on to 4.1, time permitting, okay? Alrighty. Okay, we'll see you in 10 minutes, guys. Okay, guys. So we'll do a little bit of question and answer now about the upcoming material for the exam. Then we'll move on to 4.1. We'll do some more question and answer at the beginning of the class period on Wednesday. So does anybody have any specific questions at this point on Chapter 2 and Chapter 3?
Can we do a couple of drawing the 3D surfaces and shapes?
Sure. Yeah, why don't we do a couple of those? So some more examples of drawing. quadric surfaces. And section 2.6. So here it is. So I had asked you to look at what was these? 319 to 329 odd. So let us look then at, say, and we did a few already. 326. How about 327? So in 327, which ones did I do already? I don't want to make sure I don't redo anything. It must have been here. Yeah. All right, so 321, 329. Okay, we did 329. Oh, just 321 and 329? No, there's one up here too. 319, 321, 329. So how about 327? So in 327, we've got x squared plus 5y squared minus 8z squared is 0. 8z squared. Ugh. All right, so which variable of x, y, and z, if we make would we make a constant so that you'll get circles in planes parallel, they're perpendicular to that axis? Which variable should I make a constant? Not circles, but circles and ellipses.
Set z equal to 0.
Yeah, well, it's just a constant, z equal to k. If we set z equal to k, then we get x squared plus 5y squared is equal to 8k. I have a 6 there. 8k squared. Okay, that's just a constant. Right, so I have x squared plus 5y squared equal to 8k squared. So that's an ellipse. So ellipses in planes perpendicular to the z-axis. So the z-axis is here at the origin, and then you've got ellipses that are perpendicular to the z-axis. When you slice that surface perpendicular to the z-axis, you get an ellipse. Now, the only other bit of information that you need to draw the surface nicely is going to be, what the silhouette of all those ellipses together looks like. So you pick one of the other variables, x or y, and you set it equal to 0. So if we set x equal to 0, and we get 5y squared minus 8z squared is equal to 0. Okay, well, this would be a hyperbola if this was, non-zero here, but it's not non-zero, it's 0. Right, so what does this represent? I mean, this is root 5y minus root 8z root 5y plus root 8z equal to 0. So this equal to 0 is a line. Right? So this is a line. Either this is 0 or that's 0. This is a line in the YZ plane. This is a line in the YZ plane. So you have two lines forming an X in the YZ plane with the same, the slopes that differ by negation. Right? So in the YZ plane we've got this, and then if you look in the XZ plane you get similar sort of thing. So if you want to draw that all together now, so this is X, Y, Z. So in the YZ plane, you got these lines. The X axis is sort of interfering with that. Slope it more. There we go. And then you've got your ellipses that are fitted to that silhouette. So this is a double napped cone as such. Okay. Another example, that was tree 27. Let's see what else we've got. Now, not all of these are going to have like ellipses. Like 323 doesn't. That one is just hyperbolas. I don't want to worry about that. I'm not going to ask you that in the exam. So you can leave out 323. 325. So here we've got these are all pluses. So we've got x squared plus 5y squared plus 3z squared. So 153. Minus 15 is 0. Minus 15 equals 0. So now if I move that 15 over there, I mean this, if you set any one of these x, y, or z equal to a constant, you get ellipses for every other pair. Right, so if x is equal to 0, I mean normally you would use a constant, but if x was equal to 0, then you get 5y squared plus 3z squared is 15, that's an ellipse. If you set y equal to 0, you get x squared plus 3z squared is 15, that's an ellipse. And if you set z equal to 0, you get x squared plus 5y squared equals 15, and that's an ellipse. So you have ellipses in all the cross sections perpendicular to, in all the coordinate planes. So when you have like 3 ellipses in all those coordinate planes, I mean it's just like drawing a sphere, except you fatten it up in a couple different directions, and that's what you get. So this is an ellipsoid, as it's known. Right, so just like with a sphere, you get these 3 circles in the coordinate planes. Here you get 3 ellipses in the coordinate planes. So when you have x squared, y squared, and z squared, and these are all positive coefficient x squared, positive coefficient y squared, positive coefficient z squared, then you get this. It's only when one or two of them are negative that you get these other hyperboloid type things. We did 329. That's the hyperboloid or paraboloid. That's a nice example. 330. Oh, that's just another paraboloid. I think we've gone over most of what you would see. 327. 323. 324. Is there anything else that is a good example that we should see? We've covered all the basic shapes. Let's take one more. Let's take 320. 425 and 1. Oops. Come on. 100. So again, no, they're not all positive, right? I mean, it's negative x squared, positive y squared, positive z squared. So the two variables that have the same sign are the y and z. So to find the elliptical cross sections, you make constant the one of the different sign, right? So I mean, if you have three signs, if they're not all positive or not all negative, then you're going to have two of the same sign and the third of the different sign. So that's the one you want to set to be a constant, right? So if you set x equal to constant k, then you get 25y squared plus z squared is 100 plus 4k squared. And this is just a constant. So these are ellipses in the planes parallel to or perpendicular to the x-axis. So perpendicular to the x-axis, you get these planes. So in the plane x equal to k, you get these ellipses. In the plane x equal to k, you slice that surface, you get an ellipse. So now you just let, one of those other variables equal to 0, y equal to 0, minus 4x squared plus z squared equals 100. This is a hyperbola that opens up along the z-axis, because the z is the positive variable. And then if you let z equal to 0, then you get minus 4x squared plus 25y squared equals 100. Again, you get hyperbolas opening up on the y-axis. So you have hyperbolas opening up along the y and z axes in the coordinate planes, and then perpendicular to the the x-axis, you get these ellipses, and so they're going to form right into those hyperbole. So let's see. I don't want to maybe draw. Well, we could draw both, I guess. No, it doesn't look too good, does it? So in the here, let's draw this one. So here's the hyperbolas opening up along the y-axis in the xy plane, and then here are the elliptical shapes that are going to be filling in that frame. So there's the x-axis. So this is known as the hyperboloid of one sheet. Okay? Practice those. You know, it's not really hard at all. You're just drawing hyperbolas, parabolas, and oval shapes that hug along those hyperbolas and parabolas. Okay, so you know, I mean, you just have oval shapes that are kind of slanted, and you've got a curve that follows them. Okay, so here's like a curve, and now I'm filling that in with ovals. I mean, this is all the drawing that's going on. Here's a parabola, and then we fill it in with some ovals. You know, or you've got, you know, these two lines, and you fill it in with circles or ovals or whatever. I mean, it's not hard. Now, you know, maybe you've already, you know, done quite a bit of, you know, 3D type drawing just in your notebooks when you're in high school or junior high school or junior high school, middle school or something like that. Hasn't been a thing called junior high school since I was a kid. So, but you know, for those of you that haven't, it's not a big deal at all. Trust me. All right. What else? Any other questions? On the material thus far? All right, so moving on to section 4.1. We're talking about functions of several variables. So in Calc 1 and Calc 2, you only dealt with functions of one variable. So, you know, you had one input and then you get one output. So now we've got functions that have two inputs or three inputs. So we only deal with 2 and 3 variable functions in Calc 2 and Calc 3. But you have 2 inputs or 3 inputs, and then you get one output. So number 6, for the following exercises, find the domain of each function. So here we've got fxy, x squared plus y squared minus 4. So what is the domain? So the classical definition of domain, although this is not really the modern definition of domain of a function, the classical definition of the domain is the largest set of, you know, real number pairs x, y, along which this is defined. Right, so this function is defined as long as x squared plus y squared minus 4 is bigger than or equal to 0. So this function is defined as long, well, for any x, y satisfying x squared plus y squared minus 4 bigger than or equal to 0. So that is x squared plus y squared bigger than or equal to 4. Well, x squared plus y squared equal to 4 is this circle of radius 2, centered at the origin in the xy plane. Right? We're just talking about two variables, x and y. So x squared plus y squared bigger than or equal to 4, that's the circle along with everything outside of it. Everything that's inside of it is exactly where x squared plus y squared is less than 4. Right, so this is the domain of x, y. It's the largest set of inputs along which the function is defined. 7. Same thing here. Find the domain. fxy is 4 natural log y squared minus x. So what is the domain? Well, this is defined for any x, y satisfying what? What is necessary for the natural log of that thing inside here, y squared minus x, to be defined? What's the only requirement?
Has to be greater than or equal to 1.
Greater than 0. Just strictly positive. Natural log of any number that's strictly positive is defined. So that is y squared is bigger than x. Well, if you take the curve y squared equals x, the curve y squared equals x is this parabola here. But you can't have that y squared equals x. You need that y squared minus y squared is bigger than x. Right? So this is the curve y squared equals x. So now, where is y squared bigger than x? Here? Sorry, here? Or here? Where is the y squared going to be bigger than x? Right, this is where y squared equals x. Right, so like at this point right here, right, and here's x, and here is y. So this point is x equal to y squared. So over here, what's going on? The x is less than the y squared, or the x is bigger than the y squared over here for this point?
Greater than?
Yeah, this is where x is bigger than y squared. So this is not the spot you want. So it's outside the parabola. So it's outside the parabola, but not including the parabola itself, because you need strict inequality, not bigger than or equal to, but strictly bigger than. Okay, so everything outside of the inside of that, in the bowl of that parabola. 11. Find the range of the function. So all the values over which given all the x, y's in the domain, it's all the values for g that can be obtained. So here we got 16 minus 4x squared plus y squared. Right, the range of possible values for g of x, y are what? Right, well, 4x squared plus y squared, that's positive, right? So you're taking 16 and you're subtracting something positive from it. So what's underneath the square root here is at most what?
$16.
At most what? All right, well, 16. All right, 16 minus x squared plus y squared. Well, it's got to be bigger than or equal to 0 because, it's underneath the square root in order for that to be defined. But how big can this be? 16 minus x squared plus y squared. Or 4x squared plus y squared, excuse me. Doesn't matter, actually. 4x squared plus y squared is always positive. So how large can this quantity be? Guys? 16, right? Right? 4x squared plus y squared equals 0 when x is equal to y is equal to 0. Other than that, when x and y are not, x or y is not 0, this only gets bigger. So it's 16 minus a positive quantity in those cases. So it's at most 16. So 0 less than or equal to g is less than or equal to 4. So the possible range is g going from 0 to 4. Well, not the possible range. The range is g from 0 to 4. And you can obtain any number within that. One second, guys. All right. So that was 11:14. So for the following exercises, find the level curves of each function as indicated for the value c given. And then use that to visualize the given function. So these level curves, these are like the traces we've been talking about in section 2.6, but there's something really specific. So here we have the function zxy equals y squared minus x squared, or just z. Right, and then let's look at level curves for c equal to 1. So that means you're letting z be equal to 1. So I would say z equal to 1. I don't know why they're putting the c there. So the level curve for z equal to 1 is equal to y squared minus x squared. So in your xy plane, right, this is that basic hyperbola that opens up along this here, these guidelines here. So for z equal to 1, you're getting this hyperbola. Now I'm going to erase all these guidelines. Now this is that saddle surface, you know, which becomes, you know, which is kind of hard to draw. So this is z equal to 1. So 1 is equal to y squared minus x squared. And then for 0, z equal to 0 equals y squared minus x squared. This is that x that goes through here. So that's for z equal to 0. And then this should be hugging that, using this as asymptotes. So that's z equal to 0, z equal to 1. This one looks pretty good. This one could be better. And then if you had z equal to negative 1, well, that's the parabola opening up this way along the x-axis. Because here, this switches the negative sign from the y squared, from the x squared to the y squared. So, z equal to 0, z equal to 1, z equal to negative 1. And then if you had, say, z equal to 4, it's going to be right here. This is 1, this is 2. Minus 1, minus 2. Right, so it becomes easier to look at things using these level curves sometimes. A function of a function of two variables. The graph of a function of two variables is this surface in three-dimensional x, y, z space. But instead of trying to draw that surface, sometimes looking at it through these level curves is an easier way to do so, because visualization, you know, becomes less of an obstacle. And then these level curves have a lot of special properties that we'll talk about later. But with a two-variable function, the level curves are, you know, the cross sections of that surface. So in this case, this one is like that. It's that saddle surface. It's the cross sections of this surface when you cut it along perpendicular to the z-axis. So that's that saddle surface. Looks like that. But this is something maybe a little bit more palatable to look at than this funny saddle here. 16. G of xy is x squared plus y squared. Z equal to 4 and 9. Z or G in this case. G equal to 4 and 9. Well, for G equal to 4, that's the circle of radius 2. And for G equal to 9, that's the circle of radius 3. So, and then for G equal to 1, it's the circle of radius 1. So, circle of radius 1, circle of radius 2, circle of radius 3. So that's G equal to 1, G equal to 4, G equal to 9. So, you know, you've got that parabolic rate of increase, and, you know, this surface is one that you can really visualize pretty simply. It's not that hard. Unlike those, you know, more complicated surfaces that start with that saddle. But this is that paraboloid. Right, so that was circles parallel to the xy coordinate plane, centered on the z-axis with the silhouette that is a parabola. Okay, so these are the contour map with the level curves of G of x, y, I guess it's the g-axis in this case. And, you know, this is the graph G equal to x squared plus y squared. Right, so you know, you've got the contour map with the level curves, and you've got the graph of the surface. So, you know, in lieu of having this kind of picture, you know, this kind of picture might be something with, you know, more information for what you're looking for, or the right information for what you're looking for. 20. So fxy is x squared minus y. And we have f equal to 1 and 2. So you have 1 is equal to x squared minus y squared. So this is y is equal to x squared minus 1. And then you also have 2 is equal to x squared minus y. Sorry. So this is y is equal to x squared minus 2. And then if you have 0 equal to x squared minus y, that would just give you y equals x squared. So the contour map of this thing, the level curves, you know, for f equal to 0 is just that right there, right? And then for other values of f, it's just the same thing shifted down 1 unit or 2 units or more. So if you were actually to try to graph this surface, right, what would it look like? So you have x, y, and f axes. So they're slanting kind of this way. So it's just these parabolas just moving along that line. Like so. Whoops. Not that you would necessarily want to or need to draw that, but you know, there it is. It's doable, so I'm doing it. $25. So fxy is xy minus x. And we're having f equal to -2, 0, and 2. So xy minus x. So let's take a look at these equations. So for 0, right, this means x is equal to 0 or y is equal to 1. Right, so the contour map for f equal to 0 right, so that's x equal to 0, which is the y-axis, or y equal to 1, which is this line here. So this is the contour for f equals 0. And then for f equals 2, so let's see. So 2 is equal to xy minus x. So 0 is equal to xy minus x minus 2. So I think this is x minus 1, no, x plus 1, y minus 2. No, it's not that, because it is not that. Right, because that's the middle term isn't correct. Well, goodness, what should this look like? So x times y minus 1. So I guess we would write it like this. So y is equal to 2 over x plus 1. So 2 over x plus 1, well, that is this, right? So 2 over x is either here or here. So that is the contour for f equals 2. And the contour for f equals negative 2, so this is going to be negative 2 over x is equal to y minus 1. So 1 minus 2 over x is equal to y. So, well, that's this here. So that's f equal to 2 and f equal to negative 2. So this is another type of saddle, actually. So you've got the f equal to 0, and then you've got hyperbolas. But the hyperbolas are, you know, they're aligned with the x and y axes rather than you know, aligned with the 45-degree lines. So these are this is a saddle type surface as well. But it's rotated like 45 degrees from you know, from this saddle surface. But again, I mean, this kind of drawing, whether or not you like to draw it or you're good at drawing it or not, it's not too useful. I mean, you can't really sort of see too much good information here. I mean, you know, so you're just turning that 45 degrees to get this type of saddle. But again, that drawing isn't too helpful. This is more so here. All right. 25, 30. For the following exercises, find the vertical traces of the function at the indicated values of x and y and plot the traces. Indicated values of x and y. So this is 4 minus x minus y. But this type of surface, we know what it is. This is x plus y plus z equals 4. Alright, so this is x plus y plus z equals 4. Now, when you have ax plus by plus cz equals d, this is a plane. Right, so this, we know it's going to be a plane. And one way to draw a plane, or at least part of a plane, is to look for the x, y, and z intercepts. Well, here, the x, y, and z intercepts are all just 4. So the plane passes through those 3 points. So this triangle, flat triangle, planar triangle, which contains those 3 points, that is the triangle defining the plane that is this surface here, right? So the surface is this plane. Now, of course, the plane extends, you know, in this direction and in this direction and in that direction, but, you know, I mean, if you just want to draw a plane kind of in 3-dimensional space, like, that's a nice picture. This one is tilted kind of funny, so it's, hard to get a nice drawing of it. But this triangular picture, that's a very nice depiction of a plane. Okay, that's the intersection of that plane with the first octant. So, you know, that's another standard example that we're going to be working with throughout the semester. So, you know, all of these surfaces that we're drawing in section 2.6 and in section 4.1, these are all surfaces that we'll be using, you know, time and again throughout the text in order to do illustrative examples of the mathematics that, you know, the calculus, that multivariable calculus that we're going to be doing. 31, well, it's 8:42. What do we got in time? For 31, fxy is x plus y to the third. And they're saying to look at where x is equal to 1. So for x equal to 1, you're going to get z equals 1 plus y to the third. So z equal to y to the third, or z equal to y to the third, that's that cubic function. That looks like that. That's a terrible. Shouldn't hump upward like that. So if you were to try to draw this, x, y, z, you would take that cubic function in the yz plane. So that was for x equal to 1. For x equal to 0, see if we can get a good copy that. Here we go. So for x equal to 0, we're here. For x equal to 1, we would be here. So that's x equal to 1. For x equal to 2, we would be here. So here's that line for the x's increasing, you know, in a line of slope 1, and then the surface is just following that. It's these cubics going upward along that straight line, because it's just an x here. It's not an x squared or something like that. So, well, it's kind of hard to tell what's the top and what's the bottom of it. We're looking at the bottom of it, actually. Looking at it from the bottom up. It's kind of hard to tell from that picture, but, you know, it's a reasonable look at that surface. Okay? So that's all for today. So next time, come with some last-minute questions. You know, we'll spend 20 minutes doing some question and answer, and then we'll have the first exam, okay? Make sure you have a working webcam, all right, guys? All right, everybody. Have a good night. See you next time.